Hi, my name is Walter Alexander Nahra. I'm a student at California State University, Los Angeles, and these are my notes for week 5 of CS 4540. The topic for this week is attention blocks, how they operate, and how multi-layer perceptrons work. So let's get started. Now, when it comes to the attention block, in 2017, a groundbreaking research paper was published by Google researchers called Attention is All You Need, which created a big splash throughout the fields of AI. Now, one of the topics discussed in the article is our attention blocks. They're responsible for calculating the necessary components to add onto a generic embedding as a function of its context to move it towards a specific direction that conveys distinct meanings. Now, if you remember from the previous video, we discussed how words are embedding. Now, preceding that step, the vector associated with a word, aka tokens, would be the same in all cases, regardless of the context of its usage, due to the initial token embedding essentially being a lookup table with no reference to the context. Now, now as we can see to our right with the image, we have three different examples of how the word mole is used. We have Americans who mole 1 mole of carbon dioxide and take a biopsy of the mole. Now, if I were to tell you one of these sentences to you, then you automatically would assume what type of mole I'm referring to. However, the embedding step consider all these examples as the same word, regardless of the context that it's used in the sentences. As such, the attention block is meant to push the vector of mole into a certain direction in order to apply what the word means in context to the sentences. This transfer of information from the embedding of one token to that of another can occur over potentially large distances and can involve information that's much richer than just a single word. Now, attention heads are the main component of attentions. Now, to visualize this, a single head of attention is parameterized by three distinct matrices: the key matrix, the query matrix, and the value matrix, which are filled with tunable parameters. The goal is to have a series of computation produce a new set of embeddings, E, where, in our case, those corresponding to the nouns have ingested the meaning from their corresponding adjectives. So as we can see here, this is an example of what we're referring to, especially in consideration to the key matrix and the query matrix. Now, the query matrix, first we have the query vectors, noted as Q, are a series of questions with a much smaller dimension compared to the embedding vector associated with each token encoding certain directions for that token to move towards depending on the answers of said questions. Computing this query looks like taking a certain matrix, which is notable as W with a log Q um, beneath it. Computing this query looks like taking a certain matrix, notable as WQ, and multiplying by the embedding of the word. Now, as we can see, we have the image right here. So we have the embedding, which is represented by the E column, and then we have the matrix. How it's written here is the correct way of writing it, as I couldn't really write it within text. So just note that every time when you see the words like this with a uppercase letter and then a lowercase letter, just note that I'm referring to how it's written right here, and this applies to all the other matrices with a similar pattern. So these two are multiplied, and then it creates the query vectors as known as Q. Another series of matrix, the key matrix, is multiplied by each of the embeddings in parallel to the query matrix, which we'll discuss next. Now, the key matrix are the second sequence of vectors called keys, acting as potential answers to the queries, which are mapped to the same smaller dimensional space as the query matrix. The key matrix is known as WK. Meanwhile, keys are referred to as the letter K. Conceptually, we want to think of the keys as matching the queries whenever they closely align with each other, and the method in which we measure how closely a given pair of key and query vectors align is to take their dot product. So a large dot product corresponds to stronger alignment, meanwhile, a smaller dot product corresponds to weaker alignment. As we can see in the image right here, uh, notice all the small little dots representing the dot products. So we have very small circles, which means that these alignments are very weak. Meanwhile, we have for the column creature, we have very big dot products for fluffy and blue, which means that the word fluffy and blue have a stronger alignment to creature. Attention pattern. After computing all the dot products of the key query pairs, we're left with this grid containing values ranging from negative infinity to infinity that displays a score of how relevant each word is to obtain the meaning of every word. So as we can see up here, we have all these negative numbers, and then only a few positive numbers sprinkled in around the matrix. The way we're about to use these scores is by taking a certain weighted sum along each column weighted by the relevance. This is where we utilize softmax in order to convert the range of these values to be between 0 and 1 for each column, which adds up to 1, which we can see in our second image here, how all these numbers essentially got pushed to zeros and numbers between 0 and 1 in order for all the columns to be equal to 1. If you like, say you take this column, for example, and you add it up, it'll equal to 1. Or this column with like if you add them all together, it'll equal to 1. Now, the attention pattern, which is known qk to the power of t, refers to the grid of normalized values rather than the initial grid values. So this is the attention pattern right here. There's also something called masking. Masking is a process that prevents words that appear later in the input to influence words that appear earlier by forcing these later words to be equal to 0. Now, there are versions of the attention mechanism where masking isn't always applied. That's something to take into consideration. Furthermore, the size of the attention pattern is equal to the square of the context size. This this explains why context size represents the limitation for LLMs and why scaling it up is non-trivial. Additionally, recent efforts have seen some variation to the attention mechanism that are aimed to make context more scalable as the desire for larger context windows grow. Our third matrices within the attention head is the value matrix. The value matrix, which is WV, is multiplied by the embedding of the previous word, creating a value vector called V that would be added to the embedding of the following word. Value vector V live in the same very high dimensional space as the embeddings, which are associated with their corresponding keys. Just like the query matrix, we have the matrix representing the value matrix, and then we have the embedding followed by the vector that represents the value. Now, the way the embedding associated with their respective column are updated is by adding together all these rescaled values in the column labeled as triangle E, which is just a triangle symbol, and then to the E, which you can't really produce onto written text, which is added to the original embedding, resulting in a refined vector E that encodes as a much more contextually rich meaning. Number of value parameters is equal to that of adding the number of query parameters to that of the number of keys parameters. Before moving further, I think it's important to acknowledge the fact that what we discuss is just one attention head, as attention blocks tend to have multiple different attention heads with their own unique query, key, and value matrices that are running in parallel together. So that's something to take into consideration. That what we went over is just one attention head out of like a couple thousands. Now, the multi-layer perceptrons or LMPs are entirely different when you compare them to the attention blocks. The computation in these multi-layer perceptrons uh, MOPS, are relatively simple, consisting essentially of a pair of matrix multiplications with a simple function in between. As we can see in the image up here, we can see how very simple it is in comparison to the tensor block. When entering the MLP block, each vector that was originally associated with a token go through a series of operations that will result in another vector of the same dimension. The resulting vector will be added to the original vector that flowed in, and that sum will be the result flowing out of the MLP. The vectors don't exchange information with each other in this step, as they're all kind of doing their own thing, going through the operation in parallel to each other. The first step within MLPs is multiplying the vector that flowed into the MLP block by a very big matrix, which are the model parameters that are learned from the data. Each row can be denoted as R. The vector being processed by the matrix will be labeled as E. So if we see in the first image, we have the very big matrix here, followed by the vector that's being processed, and it'll equal to a vector that are the dot products of the rows of the matrix with the vectors being processed. So an example would be that the first component in this output, the dot product R0 times E, will equal 1 if that vector encodes the first name Michael, and 0 negative otherwise. All the other rows are asking some other kinds of question in parallel, probing at some other sorts of features of the vector being processed. The first step of NLP blocks also involves adding another vector to the output known as the bias vector. The total number of rows in this matrix is something like the number of questions being asked. Since this matrix maps us into a higher dimensional space, we're going to label it as W up and the bias vector as B up. So as we can see in the second image, not only do we have the matrix and the E vector that we discussed from the first image, but we also are adding a bias vector. The bias vector in this case makes it so that it pushes the outcome of the dot product into a certain direction to produce this outcome, which will be important. Rectified linear unit, or ReLU, is a common choice to utilize in the next step of the process, where we pass this large intermediate vector through a very simple nonlinear function. If you pass in a negative value, it returns 0. If you pass in a positive value, it leaves it unchanged. So as we can see in the image right here, we have all these positive and negative numbers, but the positive numbers are unchanged. However, the negative numbers are changed to equal to 0. Often models will use a slightly modified function called GELU, which has the same basic shape, but it's just a bit smoother. The neurons within this context refers to the values leaving the ReLU, becoming active when the value is positive and inactive when the value is 0. The next step in this MLP process looks very similar to the first one, with the vector leaving the ReLU being multiplied by a very large matrix, followed by adding a certain bias vector. The difference in this step is the output, where the number of dimensions in this output is back down to the size of the initial embedding, denoting this matrix as the down projection matrix. If you remember in the first step, we went row by row, but in this step, we're going by column, which is denoted as C. So it's basically the same process as the first step, where we multiplied the big matrix with the vector, uh, in this case, the vector produced from the ELU, followed by adding a bias in order to produce the final outcome. Essentially, when the relevant neuron is active, we would be adding that column to the results. But with neurons that are inactive, if that number was 0, then this would have no effect. Also, another thing to point out is that if you have a bias in this case, it's something that's added on regardless of the neuron value. So you would add the bias in no matter the state of the neuron. An important thing to note is that down projection matrix is known as W down, which refers to as the down arrow, and the bias vector is a B down, also known as a B arrow pointing down. So essentially, the NLPs consist of two matrix products, each with a bias added and a simple clipping function in between. One thing to discuss before we end this video is superposition. The basic idea is that if you have an n-dimensional space and you want to represent a bunch of different features using directions that are all perpendicular to one another in that space, that way, if you add a component in one direction, it won't influence any of the other directions, then the maximum number of vectors you can fit is only n, the number of dimensions, which is visualized right here with the image. What if you were to relax the constraints a little bit and tolerate some noise, like allowing those features to be represented by vectors that aren't exactly perpendicular, aka nearly perpendicular, maybe between 85 and 95 degrees apart? The smaller dimensions hardly give you any extra wiggle room to fit more vectors in, which makes it even more counterintuitive that for higher dimensions, the answer changes dramatically. In general, a consequence of something known as the Johnson-Lindenstrauss lemma is that the number of vectors that can be crammed into a space that are nearly perpendicular grows exponentially with the number of dimensions. These are the videos used during the lecture and were present in the assignment document. As always, we had three blue, one brown, with two videos. The first video discussing the role of attention in transformers and giving a step by step of how the process operates, and then the second discussing multi-layer perceptrons. And then we have the remainder of the code basic video from last week, continuing off where we left off, where he discussed attentions and multi-layer layer perceptrons. And this is the end of my video. Thank you for watching and have a good day.